Good evening, all. So, warm welcome to the C-DAC web series on quantum algorithm using Qniverse. So, it's been quite a journey. Since last few weeks, we have been going through fundamentals and some more advanced concepts of quantum computing. To have a recap, so first we started our journey with a talk with Professor Apurva Patel with an introduction to the quantum computing basics, followed by Henry Sugmar giving an introduction to the QNUS platform as such. Then later we started building blocks of quantum computing as given by Naresh. And later we had Professor Anirban Patel giving quantum veto protocol, Hari giving Dosh algorithm. Then Amlan gave a talk on quantum Fourier transform. And last 2 weeks we had a wonderful session from Professor Jodhisharan with the Shor's algorithm and Bernstein Vasarani algorithms. Now, this week we are going to have a session on Simon's algorithm by Mr. Tilok Sadhukhan. Tilok is a researcher in quantum simulation and algorithm design, currently working as a project engineer in quantum technology group at C-DAC Bangalore. He holds a joint MSc in physics from Chhatrapati Shahuji Maharaj University and IIT Varanasi, and has a research experience at TCG Crest, where he worked on laser power stabilization with acoustic optic modulator and feedback control system aimed at enabling the gravimeter capabilities of measuring G with 10-digit precision. At C-DAC, he develops and analyzes Hamiltonian simulation methods such as Suzuki-Trotler composite decomposition and truncated Taylor series, focusing on improving their efficiency. His work includes implementing time evolution algorithms in Qniverse platform, creating graph-based commuting cluster methods to optimize simulations, and applying these approaches to molecular systems using Jordan-Weiner mappings. He has also published research papers on molecular property prediction with graph neural networks and created tutorials on foundational quantum algorithms to support and training of new researchers. So he'll be giving a detailed talk on Simon's algorithm in today's series. So over to Tilok.
Am I audible? Yes. Okay. So yes. So hello everyone. So good evening to all. So firstly, I want to thank all the organizers for giving me this opportunity to present about the Simon's algorithm webinar series that it is currently going on in quantum algorithms using Qniverse. So throughout this webinar, I'll try to highlight the key topics of Simon's algorithm, outline the key idea behind it in details, and also try to highlight what it is and what it is. So just to give a brief context about, so in 1994, Daniel R. Simon introduced this algorithm. So it is quite historical. It is quite historical because it offers exponential separation between the classical and quantum computing. So Simon's problem is foundational example of how quantum algorithms can offer speed ups for certain computational problems. So, as it is proven to be solved exponentially faster on quantum computer than classical computer. So, whether you're a beginner or have some intermediate knowledge of quantum computing, so hopefully throughout this PPT and at the end of this PPT, you will have a basic understanding or a basic intermediate of understanding about what is this algorithm and what uh, the how it actually works. So, before uh, So before going into the details of the Simon's algorithm, firstly, I would like to highlight a very basic concept, that is what is a function. So a function is basically a rule that assigns to each input of a domain to a output of the range. So if we can consider our domain is A here, and we can then consider our range is B. So a function is basically a rule that maps each and every single input of the domain to the range. Now, just to give an example, so here I have taken two examples. One is an algebraic function of x square, and another one is the trigonometric function of sinusoid of x. So, as you can see, the domain of x square is basically all the natural numbers. Um, so, all the natural numbers, and the range of this function x square is also natural number. So it maps each and every inputs of the natural numbers to particular some outputs uh, to the range that is also belongs to natural numbers. So natural numbers all are the numbers which are basically 1, 2, 3, 4, 5, 6, 7, that is countable. So similarly here I have taken another example of sinusoidal function. So where x is all the real numbers, which is our domain, and the range or the uh, range of the sinusoidal function is lies between -1 to +1. It cannot exclude or it cannot go beyond this because we know that sine always gives uh, uh, like sinusoidal of any value always gives a the value between +1 and -1. So if we have an idea about what is a function, now we can proceed towards yes. So what is a two-to-one function? So just like a function, a two-to-one function is basically for two of the inputs in the domain, we have a single output which belongs to the range. So just like in the example that I tried to show here, which is here for each of the two inputs, there is a single output corresponding to the range. So here x1 and x2 corresponds to y1, x3 and x4 corresponds to y2, and x5 and x6 corresponds to y3. Uh, so this is a very basic example of a two-to-one function. So or more like a demonstration of a two-to-one function. So if we have this idea of the two-to-one function, so next we can proceed towards the main problem of Simon. So so the Simon's problem, the problem setup follows like the way it is being described here. So as I just have described what is a two-to-one function. So the problem is we are given a two-to-one function where if is the inputs are all the bit strings, where we are dealing with binary numbers and outputs are also binary numbers. In spite of, so in the previous examples, I have shown you the functions which are actually examples of basically decimal numbers, but here I am trying to give an example of binary number. So for which there exists a secret string s such that for all the inputs that belongs to x, fx is going to be x bitwise x over s. Now, so fx is the output of our the input that we are giving, and for all the inputs, that is x belongs to 0 to 1. So x belongs to this input string, uh, and also following this condition, there will be a secret string s. Now, using Simon's approach or Simon's algorithm, we are essentially trying to find out that secret string by using the Oracle queries to f. So that is the main agenda of the whole idea of what we are essentially trying to do here in Simon's algorithm, which is just to find out the secret string s. Now, just to give an example about to make things more intuitive and more like so that you can visualize actually what more precisely. So here I have taken an example of n equals to 3. So as you can think that if n equals to 3, so then all the possible number of inputs would be 2 to the power 3. That is number of 8. So that is 8. So here I have outlined all the possible number of inputs. The total number of are 8, and there will be corresponding outputs also. Now, since we are dealing with a like binary numbers, so here the function is also a binary function. So and as I have just discussed before, that the function has to be a two-to-one function. That is the promise we are starting with from the very beginning. So you can see here for each of the two inputs there exists only one output. So as you can see 0 0 0. So for this input we have a single output 0 0 0, and for this input also we have a single output 0 0 0. So for these two inputs, we are getting a single output. Similarly, you can see for all the inputs, if you look very carefully, there will be a 2 to 1 correspondence. So which essentially means that this is a 2 to 1 function. So our bit string is hidden. That is our age, which is 101, and we will try to find out the bit string. Now, uh, uh, now you might think that what exactly or why we're trying to use Simon's algorithm to solve this problem, to solve this query problem actually. What is the point of doing all this algorithm and stuff, of doing understanding this all this so there is actually advantage of uh, approaching this problem using algorithm rather than classical. What is this advantage? So you see, as I have told that for n equals to 3, there will be 2 to the power 3, which is 8 outputs. If we generalize it to n number of n's, we'll have a total capital N number of outputs. So if we try to solve this problem using a classical computer, so we need the input values one by one until we encounter repeated output, right? So if we just put this our input, and then we're going to again put the second input, then we're going to again put the third input, and we're going to repeat this process until and unless we encounter some repeated output. So you see, for the worst case scenario, what we will get is basically for the worst case, we might have to go more than the half of the time. For example, here we have outlined 8 inputs. Here, the inputs, the number of the inputs are 8, right? So in the worst case scenario, we have to go at least 5 times to confirm that we are getting the repeated out. So if we try to generalize it, we are getting actually 2 to the power n. So I just try to write it down here. Uh, 2 to the power n. Okay, it's not working properly. Okay, fine, no problem. I'll continue. So you can see here 2 to the power n divided by 2. So that is basically we have to run a total number of we have to run the query a total 2 to the power n minus 1 times plus 1 times basically. So this means is 2 to the power n divided by 2 and plus 1. So that is the half of the times of the input number of the inputs. So you see, if we try to solve this problem using a classical approach or classical computer, we have to run or you have to run the query to the function at least in the worst case scenario 2 to the power n minus 1 plus 1 times. But whereas in quantum algorithm, if we try to solve this using a Simon's algorithm, so we will be solving this problem by a single query. So that is the advantage of using Simon's algorithm for this particular problem. So here I have just tried to outline actually what are the gates are and what are the circuit diagram are. Now later in the following slides, I'll go each and every single step in very detail just to give you an outline about how this algorithm is been implemented or at least have an overall structural idea about how it can be done. Is basically we start off with two registers at zero with the we are dealing with some generalized case. We are dealing with n number of qubits. So here I have started off with state 0 and 2 registers, and then I'm just applying some set of Hadamard gates to create the equivalent superposition of all of this input that I'm getting here. And then I'm just adding these two states into an oracle. Now, what is an oracle? Oracle is basically it is a black box. It is defined in this way. Basically, that is, if the inputs are x and y, the corresponding output will be x and y bitwise XOR fx. So that is our oracle, and that is how it is defined. And the corresponding output is going to be shy2. So this would be our shy0 that we have started with. This is shy1. This is shy2. Now, once you have got the shy2, now there is a very tricky part. Later, I'll try to explain it very details. Which is then we're just trying to collapse. So if we apply some measurement gate on the second register, the whole state will collapse into this particular state. And finally, if we just put another set of Hadamard gate, we will get some possible states for which this condition particularly holds. Now, if we try to stack that into a single row, sorry, if we try to stack that all the rows basically into a matrix and try to solve it, we will get essentially we'll get the secret string. So that is the main essence or main idea behind this algorithm. Now I'll just start going into the details. So here, step one is, uh, as you have said, some of you have already are aware about what actually Hadamard operation does to a qubit, or what actually Hadamard operation does to a state. So it creates equal superposition of all the possible states. So if we consider a single qubit, so if we just apply a Hadamard gate on the gate 0, it is nothing but it is creating a superposition of both of the states, right? So as I have just said, we are beginning with the two of the registers, which is gate 0, and our initial state we are assuming as gate 0, tensor product of n, and then this is tensor product of gate 0 for n number of qubits. So so if we just generalize this concept about applying the Hadamard gate on a state creates equal superposition of all the possible states. Um, um, that state has to be a zero state, of course. So by applying the Hadamard gate H to the top register, we are basically creating an equal superposition of all the possible states. So we started off with a zero state, and then applying the Hadamard gate, we are basically creating the equal superposition of all the states. So here the x is basically the number of the states. Basically, it represents the number of the states, the nth number of states. Basically. So x will run from 0 to 2 to the power n minus 1, as we are dealing with n number of uh, nth system, as you are dealing with a system with the n generalized value of n. So we have a step psi 0, which is this, and then applying the Hadamard gate. I have just tried to show it in the circuital form to have a more intuitive understanding. So psi 0, and then we're getting a psi 1, which is nothing but just like this. This is our state after the Hadamard gate. Now, after the Hadamard gate, we're just applying the oracle. Now, what is the oracle? Just like I have described, just I have told previously also, the oracle is just a black box unitary that implements the function f via bitwise XOR. So this is the way the oracle is defined. So if the two input registers are x and y, the corresponding output registers will be x and y bitwise XOR fx. Right. So we have started from the uniform superposition of psi 1, that the last circuital part that I have shown here. Here we are getting actually psi 1. Then we are applying the oracle. So after applying the oracle, just following this definition, we will get basically the second part of this uh, second part of this state will be y, which is our y is what? Y is 0. That is our 0. Right. Sorry. So that is our 0th state. So no matter whatever state you do a bitwise XOR with a 0th state, it will always be the exact state. So that means, so if you do like 0th state bitwise XOR with any state f of x, any random state, so it will always be f of x only. So no matter what the state we are dealing with in that particular function. So because 0 bitwise XOR operator is basically that particular thing. So that is the same thing that has been done here, which is our x, and so again the 0 bitwise XOR fx results only fx, get fx. So that is our psi2 that we are getting here, and then we are applying a set of measurements, a set of measurement get on the second register. Now this is a very tricky part, so I'll try to explain it with a way as simple as possible. So so as in the previous after the oracle, we had this state psi2, right? Psi2, which is of this form. So we are putting the psi2, and uh, and we are just applying the measurement gate. Now, if we apply the measurement gate among all the possible states, only once we will get only one state. For an example, this is our fx. This represents our fx. So if we apply a measurement gate, so it will collapse into one particular state, right? So x0. So if we assume it x0, now imagine what you have started with the initial problem statement of the Simon's algorithm, which is for each of the two inputs there will be corresponding one single output. So just like here, so we have a one single output that is our f of x naught. Now, uh, just the promise that you have started with, so there correspond, so, so it corresponds to basically two inputs for this particular state. So we have get of x0 and get of x0 bitwise x, right? Bitwise XOR s. So these two possible states are only surviving. Rest is gone. Why? Because we have applied this measurement gate on the second register. So just for that reason, we are getting a equal superposition of these two states only, right? So we have x0 only, and based on that, we are getting x0 bitwise x1, just like this state. So then we are just again applying some Hadamard gates on the first register. So just if you have understood it, then this psi3 that we are starting off here with. So then we are again applying the Hadamard set of gates on the first register. So what it does is basically it creates again the equal superposition of all those two states, right? So, so just so as we already know that the Hadamard basically creates an equal superposition of all the possible states. So if we try to write it mathematically, uh, yes. So if we try to write it mathematically, how the state will look like is basically, so this will look like nothing. So if we apply the Hadamard gate on the psi3, so from this particular state we'll get -1 to the power x naught dot w, and the corresponding states are along the way. So similarly for this state also, we will get this some kind of the same expression. And now from this, we are just, if we follow a little bit of algebra, we are just getting from this equation to this equation. Now how we are getting this, like, I'll just explain in the next slide. So just remember that this is the expression that we get basically after the uh, second set of atom on the first register. So these are the two properties that I've used here to simplify this expression. So these are the x bitwise x dot y with the dot product. If we apply this, we'll get basically x dot w and bitwise x dot y dot w. And this is one more property. So if we now, these properties are a bit different because in comparison with the classical, or in comparison with the um, uh, uh, decimal numbers, since we are dealing with binary numbers, so these properties are a bit different from whatever we are familiar with in the sense of our regular algebra that we do. So just like I've said, our last state was this type 4, which is of course in this form. Now if we simplify this using these two relation, we'll just basically get these two outputs. Now if we just take this part common, we'll ended up getting this part. Now, so therefore, so from this state, if we simplify it basically by doing some bit of algebra, so we'll get this state. So you see the ket psi 4, whatever the state that is coming here, the amplitude of those states depends on this factor only, right? So no matter whatever it is coming, of course it will not coming, it will not come all the possible combination, but uh, from those possible inputs, some very few will occur, and for all those states, this condition will be uh, holding. So now we are going to deal with this thing only from now onwards. So the possible two outputs of S dot W is going to be either 0 and 1. So so if it is a 0, so you see if it is a 0, then it becomes 1 only, this part. But if it becomes 1, then you see it becomes 0. So that does not count at all. So only we are going to get only those states for which S dot W equals to 0, right? So for those states, for those S dot W equals to 0, the W's are going to be surviving. So just which mathematically I just tried to written it here. That is for those case, S dot W is going to be 0. Only those terms will be surviving. So yeah, so just repeating it in a very formal way, which is what measurement gets basically give is each run returns a bit string W with W dot S basically WI dot SI modulo of 2. Now we are going to repeat this experiment. So there is a possibility that all the W's that we are getting here may not be linearly independent. So remember our main goal was to find out the value of the secret string, that is our S, right? So to do that, we are going to we are going to form a set of linear equation, or we are going to form a set of linear equation basically, which will give us the secret string S, right? So it is not necessary that we are going to get all the possible outputs which are linearly independent. So we are going to get only, we may also get linear independent also. So that is why we are going to repeat this experiment, or we will repeat this circuit iteration until we get the n independent strings. And then based on whatever surviving those W's are, we are going to stack them as a row of a matrix. And then if we just stack it, we are going to get a W a matrix which is W. And if we just solve it, this homogeneous system W dot S modulo 2, we are just going to get this our secret string S. That is how it is done. So just before going into that how this system can be solved, I'll just once again recapitulate about the Gaussian elimination, which is a standard approach for solving a linear system, and not also standard, very simple. So um, just a review of the Gaussian elimination, which is if we have a set of linear equation, that is, let's say we have these three equations, and if we want to solve it, then we can follow the Gaussian elimination process. So so what we do is basically in Gaussian elimination is we try to write down this augmented matrix with all the coefficients along with the the right hand side of these equations, and we perform some kind of operations, either row operations or multiplication with any rows. Whatever operations we want to apply, we can apply. But our end goal should be, this matrix has to be in some form, so that we can just omit the, like, in a beneficial way we can solve it. Basically, we can do a lot of we can do a lot of idea sorry we can do actually a lot of things with it. uh, so yes, so we have this system of linear equation, and after applying the row operations, we can get either two of the states. So we can get either two of the matrix form, which is one is this and another one is this. So if we try to solve it, then we'll get basically we're going to essentially solve it. So based on our requirement, or based on whatever we want to do, we can make that matrix form, but we have to make it in a suitable way, so that we can actually solve it. Basically, that's it. Yeah. So, but in the case of this system that we had, w dot s equals to 0 of module of 2, we are dealing with only binary numbers, not decimal numbers. So previously, whatever example I have given, it is dealing with decimal numbers only. So, and in the case of decimal numbers, to transform the augmented matrix to a echelon or a upper triangular or whatever diagonal form of the matrix, we can apply any operation, or we can add it or remove it, any like any sort of operation we can do. But here we are restricted. We cannot apply any operation in when you're dealing with a system of um, binary system, basically. So, just like that was our main goal, to solve to w dot is equals to 0. So how can I solve it? We just stacked our possible outputs, and later I'll just going to explain again how I'm getting this all these three rows. But for the sake of assumption, let's just assume it for the w we are getting is this. Now we are going to solve this homogeneous system, which is w dot s. Now we have assumed our s, which is our secret string, which is s1 s2 s3, as a column matrix. Now if we try to solve it, we are allowed to apply only these kind of operations. So we can just swap the rows. We can row addition. Now here the row addition means that we have to apply the bitwise XOR operation. It's not just a simple that you can add the two rows. So when we say that we are going to do the row addition operation in the context of binary numbers, so we are essentially mean that we are going to apply this bitwise XOR operation. So uh, just the rules are is 0 bitwise XOR 0 is 0, and 1 bitwise XOR 0 is 1, 1 bitwise XOR 1 is 0. Similarly, 0 bitwise XOR 1 is also 1. So for the variable, when the two inputs are different, then we are getting only one. In the rest of the case, we are getting 0. And one more property which is very important, which is no scaling. So we cannot scale it, because the only two possible numbers in the binary system is 0 and 1. So we cannot scale it. We cannot multiply with um, any number actually. So just like how this can be solved is, we started off with this matrix, then we just swap the r1 and r2, so which gives us this, and then we have applied the r3 bitwise XOR r1, so which gives us this matrix form. And then we are getting the R3. Then we are applying again R3 bitwise XOR R2, again another operation, and that gives us this. And you see, from this matrix form, we can proceed further also. We can do some other kind of operations also. But you see, from this operation, from this kind of matrix form, we can actually solve it. We don't need to go any further, or we don't need to put any further uh, operations. So we can actually solve it by putting the S. Now, just I have assumed my S is a column matrix of S1, S2, and S3, and so from this, if I just try to say it, so this is my W matrix. Here will be a column matrix. So here will be a column matrix where it will be S1, S2, and S3, right? So if we just do the multiplication, now here the multiplication also means the bitwise XOR. So 1.1 bitwise XOR 0.1 uh, dot bitwise XOR, sorry, bitwise XOR 1.1. So which basically results something here like this. So here we are getting if we just simplify that first equation and if we apply the second to the this row, so what we'll get is 0 bitwise, 0 dot 1 bitwise x or 1 dot 1 bitwise x or 0 dot 1. So if we just try to simplify these two equations, we'll get these two equations. Like first equation is this, the second equation is this. S2 is 0 and S1 and S2 is going to be equal. Now, if S1 and S2 is going to be equal, only there are two possible values. Either they can be 0 and they can be 1 only, right? So if now here is a little catch, which is S1 cannot be 0, because if it is 0, then S3 also 0, and then the whole string is 0. But to begin with, where we have defined the Simon's problem, we were excluding that secret string, which is 000. We are excluding that string from the very beginning. So it cannot be, we have assumed it in this way. So it cannot be 0, it has to be only 1. So similarly, if we assume it a 1, then our bit string, we have just recovered it with 10. So that is a standard procedure of finding the secret bit string using the Simon's algorithm. Now, just a quick verification. Thus, so just I have claimed it. If this is this, it has to satisfy that homogeneous system of equation, right? So here is a W. I have taken it again, and I have just done the multiplication. W dot S is just simple 0 dot 1 bitwise x bar 1 dot 0 bitwise x bar 0 1. And similarly, from the other cases also, we are just going to get 0 0, which essentially satisfies our homogeneous system. Now, now I have tried to make things more intuitive and more simple, or maybe for the sake of understanding, I have taken for value of n equals to 3 and tried to showcase whatever you have done throughout the previous slides. I'll just repeat it for the n equals to value 3. So this is the prerequisites that we have taken. So we have taken the top register is 0, the bottom register is also 0. Uh, so we have a three n equals to 3 system. So the initial state should be 0 0 0 get 0 0 and get 0 0 0, and the hidden string is 101 that we are assuming. Now this is the promise that we have already um, uh, we are starting with. So fx has to be equals to fx bitwise x or s, where s is a secret string and x belongs to a bit string that has the length of 3. So just I have described it previously also. So we started off with this state only, which is all the possible. So the get 0 states only, and then we applied the Hadamard state on the first register, then which creates an equal superposition of all the possible states. Now here we are dealing with n equals to 3, so that's why we are getting the coefficient of 2 to the power 3, that is 8. Now it will run from 0 to 2 to the power n minus 1. So the joint state becomes the tensor product of this initial state, that is our get 0 0 0. The joint state becomes psi1 is 1 by square root of 8, all the possible combination of x and 0 0 0. So now each of the 8 2-bit strings x is now equally present on the top, bottom is untouched so far. So that is, yeah. So now we are putting the states into the oracle. So the oracle is just like I defined it, x and y, and the output is going to be x, y, bitwise x, y, x. Now again, my y is what? My y is 0, right? So my y is 0, so that's why it will be always be fx. 0 bitwise x or fx is always be fx. So my shy2 is going to be this. After the oracle, I'll be getting this one. Now, if we just measure the bottom register, then if you just measure the bottom register, and I'm assuming that I'm getting the outcome as 0 1 0. So then the top must one, so the top of the register must be one of the two inputs that map to that particular value, which is either 0 1 0 or 0 1 0 bitwise x or 1 0 1. Why? Because 101 was our secret string that we have started with, that we assumed. So we will be getting a combination of these two states only, right? Because it has collapsed already into this state. And for this particular value of fx, there corresponds two values from the inputs. And those two values are 0 1 0 and 1 1 1. So, so after applying the measurement gate on the second register, we are going to get the state this on this form, which is, of course, we are dealing with only the first register. So, yeah, after doing the measurement, we're getting this. So And yeah, so just mathematically, if we just apply the Hadamard gate on any state, mathematically it will look like in this form. So if I assume my x is my state, uh, that represents the inner state basically, where we have assumed three for the three qubit system. So it will take basically in this form. So W will run from 0 to 2 to the power 3 minus 1, which is 0 to 7, and it will create basically all the superposition of the states, and this factor actually ensures the signs actually. Yeah. So hence, the amplitude of the W after the second Hadamard is going to be proportional to this factor. So just like I have described previously, that this minus 1 to the power 0, 1, 0. So we had this state that is 0, 1, 0. And another combination is 0, 1, 0 divided x squared 1, 0, 1, which is 1, 0, 1. So I have taken this form only. So you can see, and of course, we started to make it to make our understanding be simple, that we already assumed s equals to 1, 0, 1. But in the real case, we actually don't know what is our s, right? So you see, if I just apply the properties that I described uh, here, these properties I have used, and using these two properties, oh, sorry, using these two properties, if I just simplify this form, we are going to get this form only. So our amplitude basically is proportional to this factor only. Now, as I've just said, h dot w has to be either it has to be equals to 0 or 1. So if it is a 0, then those terms will be surviving, and if it is a 1, those terms will not surviving. Will kill that off. So by following this, we will get our W that is going to be surviving are these four states only. So our W is basically these four states, and it will create an equal superposition of all these states, right? So because we are applying the Hadamard, so all the probability that is we will be getting is each of the state is 1/4, and rest of the states are gone because S dot W is 1 for those cases. That's why rest of the cases are 0. So key takeaway from this is one run gives a random W satisfies W dot S. So we'll repeat this process to collect our uh, W, so that all the W that we collect are linearly independent. So until and unless we are getting these linearly independent Ws, we're going to repeat this process. So in this way, once you collect the linearly independent Ws, then we can proceed towards our solving the basically capital W matrix, which is we'll be solving this homogeneous set of linear equation, that is W dot S equals to 0, where we are going to get the S, which is our secret state. Now, here is a circuit diagram, or like the intuition of the circuit of the three qubit system. Three n equals to 3 system. So we will require 6 qubits in total. So we are applying the first set of Hadamard gate on the first 3 register. Then we are applying the oracle, and here I have applied the set of measurement gate on the bottom register, and then I have again applied the set of Hadamard gate to create the equal superposition of uh, all the possible states, which is nothing but the two states that is existing here. So we are not getting all the possible state that we have started with here. We are getting only two states, one by square root of. So if you can remember, one by square root of uh, the state that we are getting here is 1 by square root of 2 x0 get x0 plus get x0 bitwise xor s. That is the state we are getting here. And if we apply again Hadamard set of Hadamards, we are going to get superposition of all of the states, and only those terms will be surviving for which s dot uh, uh, basically s dot w w dot s or s dot w is going to be 0. So here is the intuitive circuit. Now, one major challenge for this algorithm, or uh, one major aspect of it, is to how to design this oracle. Now there are many ways actually how it can be done. So and there are many ways. I have tried to explore this way only. So you see, if I apply a set of C node gates, um, just like this combination, there's a like we if you ask me that why am I applying this in this way, so just to give the answer to that is our main goal was to get the state which is of that form of uh, that was our fx, right? State of fx, and we had this x and equal superposition of all these states. Like our main goal was to create this state, right? sorry. So our main goal is to create this kind of state. So if you just write down the state in the mathematical form and apply the CNOT gates one by one, uh, by following this combination, we will going to get exactly this state. So, but it's not mandatory that we have to follow this way only. There are other oracles, other form of the uh, combination of the CNOT gates also we can get, or we can um, implement to get the same kind of result. So yeah, just like I have tried to show the mathematical side of it. Look. So before the Hadamard, we started off with this. Yeah. So before the Hadamard, we started off with this initial state that is was Shine. So it creates equal superposition of all the states, and our rest of the registers were zero. So that is why that you see the rest of the terms are zero. Only it includes all the possible number of the states of the first register only. So in the second register, I have tried to apply the C0 gate from x0 to y1. Now, this is my x0, this is my x1, and this is my x2. Similarly, this is my y1, this is my y2, and this is my y3. So see, after applying, we're going to get this kind of state. And then again applying uh, the from Q1 to Q1 to basically Q4, I'm going to get this state only again. And if we just apply accordingly the kind of operations that I have applied here, we're getting the exact same state that we are supposed to get. So there are other methods also exist, of course. So I would urge all the participants to explore those things also. Like maybe you can send us some feedback on like if there are any other. Of course, there are other ways. So you can think on those things. Yeah. So if we just try to sum it up about what exactly the Simon's algorithm is basically. So our main agenda was to find out the hidden bit string. That is yes, and we started off with a promise that uh, our function has to be a two-to-one function, and it has to satisfy this property, which is fx, which is f x bitwise x or x for all the possible x, where x is or all the inputs. Now, just like I'll repeat once again. So we had this promise from the very beginning. That is our f, which is our function, is two-to-one function. And also, I forgot to mention here one more promise we started with. Oh yeah, I have mentioned it. Okay, sorry. So S, which cannot be a combination of zeros only. So then how we have tried to achieve, or how we have tried to solve the bit string is basically I have prepared the get zero states and then applied the hammer on the first register. Then we applied the oracle, and then we have applied the measurement gate on the second register, and after that we applied the hammer gate on the first register, which gives us basically those values of w which for which s dot w equals to uh, uh, 0, right? So by collecting the w's, by collecting this equation s dot w equals to 0, we are going to stack up basically a matrix for which all the w's are going to be 0. For all the exist all the for all those w's, the w dot s equals to 0. That has to satisfy, right? So in this way, we are just creating a set of a homogeneous system, and if we solve it using a Gaussian elimination, we just essentially getting the um, yes, yeah, we are essentially getting the final um, hidden bit string that we are looking for. Now, what is the advantage? So the advantage is if we try to solve it using a classical approach, so we have to at least go more than half of the inputs in the worst case scenario. So that is 2 to the power n minus 2 of the order of this. So and you have to go query function f one by one, and you have to repeat this process for the worst case this much of time. But in the case of this algorithm, we can solve it actually using only one single query. Uh, so I hope you have a good yes. Yeah, I hope you have a build understanding about what is the Simon's algorithm and what we are trying to do with this algorithm. And uh, just so some kind of practical use cases, if we try to incorporate. So Simon's algorithm itself does not directly has any practical or industrial application, but it's more like a like other algorithms, other basic algorithms like Deuce Joshua, Bonston Vezzarani. Like these kind of algorithms, it is a kind of a toy model for understanding the advanced quantum algorithms such as Shor's algorithm or Grover's algorithm. Like it helps us to build the foundation. Uh, Even though it does not have any physical implication, or even though it does not have any direct uh, uh, problem solving capability, but it helps us to understand things or make our uh, groundwork better. So these are the references I have used, in case uh, you are willing to know that. So, and you can contact me with this in my email also if you have any doubts. Now I'll just quickly go into the Qniverse to demonstrate the algorithm that is already implemented in the Qniverse. So, mm, yes. So, a Qniverse is, yes, I hope I'm visible and audible. Yeah, fine. So, so Qniverse is a platform developed by our team C-DAC, where we can run algorithms, various kind of algorithms, and we can play with different kind of gates to do different kind of operations, or different kind of, in the context of different kind of algorithms. So there are already a lot of algorithms. Not audible. Audible. Huh? Okay, fine. So so if you go into the after logging in, if you go into the algorithm section, here you can see all the algorithms that is already implemented here. You can explore, and you can play with this kind of algorithms, and what kind of you can do your own analysis, whatever you want. So, uh, so you see, I just like I have given the example of a three n equals to three system. So I'll just stick with that only. So here I have a, let's say I have a three qubit system, and my hidden bit string that I told, or that I have assumed is 101. Now, if I load the circuit, you see, this is my circuit basically, right? So just like I have described. Now, this is my oracle. The oracle, just like I have described it in the my PPT, that the oracle wide is, so it not necessarily has to be in this form. You can design your own oracle until and unless it satisfies the requirements that we are whatever we are just trying to get from outside of the oracle. So that is our main agenda. We can design our own way, but here it has been done here in this way. So you can see here, first we are applying a set of Hadamard gates on the first three registers to create a equal superposition, and then we are applying our oracle, and then we are applying the Hadamard set of Hadamard gates after uh, the oracle, um, where the only two possible terms that we are getting is to create the equal superposition of all these possible states. Now we are again measuring those states um, to get the possible combination of W's that we are willing to do, basically. So if we just click on run, uh, so we will, is it? Yes. So if we hit the run button, the circuit is already is running, and we can see the status here. So for that particular n equals to 3 system, um, all the, yes, here we have got. So you see, these are the possible values of W for which S dot W equals to uh, 0. So these are the possible four values, right? So for which S dot W equals to 0. Now there is a post-processing part that is involved, that just I have described it, uh, through solving, like to get the hidden bit string, we have to actually solve that homogeneous system W dot S equals to 0. So these are the possible values of W. Now, if we just uh, take this value and go into our post processing part, which is to solve that homogeneous system. So This is our post processing part. And if we just the counts here, and which one? Python 3? Oh, where is it? Yes. Yeah. So, pardon for flashing there, I guess. Yeah. So, so if we just paste our post processing results here, counts, um, we will just create our hidden bit string. Um, that is our 101. So that is what we have started with, uh, which is our secret string. That is our 01 that we have started with, right? So if you can remember, so that actually explains the Simon's algorithm, and the PPT will be shared with you after this presentation, and you can ask all of your doubts. If you have any doubts, you can contact me. My email address is already mentioned there. And right now, if you have any doubts right now, you can ask me in the comment section.
You can type in your questions in the chat box now.
A lot of questions. I have the same question. What? Why there is no measurement done? Okay, yeah. So it does not matter actually why there is no measurement done of below 3Q register like this here in the slides. Yeah. So it does not matter actually. So if you see, huh? Share file. Huh? Yes. So if you actually see, wait, yes. So if we actually see, so these four states, uh, four set of states we are getting. So among that, only one will be surviving. So if we apply the like set of the measurement gate on the first register, sorry, the second register. So it does not really matter. So so we can say that if you do the if you follow the if you do the mathematics, or if you do the state calculation piece by piece, you can see like you can do that also. So okay, I'll do one thing. I'll just try to do this here only. Wait, no, yeah. So where is the state? Where is it? Where is it? Where is the measurement gate? Yeah, here. No. Yeah, to put it into some different. Yes, so actually, if you do this, you will get this idea basically that I have to put this in a different register actually. So, so all the possible only those ones will be surviving. So we'll have a four set of these things, and we'll get only one set if we apply the measurement gate. Uh, and since we are dealing with this uh, Hadamard gate, so we'll not basically have any problem with it. Where is the second question? Yes. Okay, so hi team, how started with a certain value and finding what is by the questions. Okay, stop. Fine. While loading. We, okay, okay. Yes. So hi.
Sorry, you have to. No, he said he will. Actually, it is you have to ask. Tilak, there is one question from Bhaskar asking how to get coherent answers using Simons with
How
Juice
to
algorithms.
using Simon. Sir is asking something. I can't hear it.
Yeah, Mr. Bhaskar is asking how to get coherent answers using
Okay. Yes,
Simons.
my mic was actually so I was not able to hear. Yes, sir. Mic and speak. Yes, sir.
Did you
Can
hear?
you repeat, sir?
Hello?
Yes.
Yeah, Tilak,
You.
there is one question asked by Mr. Bhaskar. He's asking how to get coherent answers using Simons-Joshua algorithm. Can you share using the Schrodinger's cat example as a dependent and independent one on both the same time? So if you can,
Hmm. So to get coherent answers using Simon's with Joshua algorithms, can you share using the Schrodinger's cat example as a dependent and independent are both at the same time. So I think it's not, to be honest, it's not clear what he's trying to exactly know. So how to get coherent answers? What do you mean by coherent answers? Can you, if you can, coherent answers using Simon's and Joshua algorithms? The Schrodinger's cat example. No, actually, the question, the frame of the question is, I feel like it's you haven't framed it properly. So if you have the doubt, you can ask it. Like the question is not clear. Uh-huh. Okay, next question. We started with a certain value of s and end we are finding what is and what is the actual value of the algorithm. No, we have to demonstrate using an example. I have tried to show with the value of s, but in real, when we are actually implementing the algorithm, we don't know actually what is the value of s. So that's why we are solving that last set of linear equation. So w dot s 0, we are setting up that homogeneous system, trying to solve it. Through that, we are actually getting what is the value of s. So just to showcase as an example, I have tried using a value of s to begin with, but when we're implementing, we don't know actually the s. So I think that gives you an answer why there is no, yeah, that is also in the oracles there on the fourth and fifth not gets controlled by the registers because we wanted to encode. No, no, the yes.
Tilak, you can read the question also. Which one your answer?
Okay, so here is another question by Vishal Pandey. Also, in the Oracle circuit diagram, the fourth and the fifth CNOT gets controlled. The Y1 and Y3 registered is it because we wanted to encode the secret string 101. Uh, yes, what fourth and fifth CNOT gets controlled when Y1 and Y3 registers. Uh, no, actually, we can do whatever we want, and like we can design the Oracle in our own way. But, if the condition is satisfied, so you can design your own Oracle as well. Okay, so any questions? Just wait. Share. Yes. So just to answer that question, uh, which is the if you just write down the mathematical form of that, like the Oracle, how to design that Oracle. So we had this. Uh, we wanted to get this output, right? So we can design the Oracle as per whatever we want. So we can just write down the step by step. states at a single time and operate each of the CNOT gates at a time. And we can see that at the end of it, we are getting this. So in this in between process, we can apply any CNOT gates or anywhere wherever we want. But the condition is you have to get this. So that's up to us. Whatever we want to do, we can whatever gates we want to apply, we can apply in terms of CNOT. Yes. There is no more question. We have
Any more questions?
two, three questions. I saw. Okay, fine. I think it's done.
There is a question, Vishal Pandey. Why does the function have to be 2, 1? 2, 1 is
2 to 1. Hey, come here. I'm unable to see them. Come on.
Yeah, why does the function has to be 2 to 1? Vishal Pandey is
Okay.
asking.
So 2 to 1 function, it has to be because the promise of the Simon's algorithm is we are dealing with 2 to 1 functions only. Like that is our assumption to begin with. So it has to be a 2 to 1 function. It cannot be 1 to 1 function. So yeah, that is our assumption that we have started off. So we cannot question the assumption. So then there is no point of solving that problem. So for that particular assumption, we are solving that problem. Now you are asking the assumption why you are assuming it. That does not make sense.
So there is Ajil Matthew asking like, can you show an oracle design by starting with an arbitrary code?
Right now, I don't have any, but if okay, if you can contact me. I'll share some the ideas. Right now, I don't have the maybe right now.
Yeah.
Yes.
Now Nasim is asking, according to Simon algorithm, state 0 will be collapsed with others. How it will work in measurement gate and what will be the output?
Sorry, sir. Can you repeat the question?
According to Simon algorithm, state of 0 will the state of 0 will it be collapse with others? How it will work in measurement gate and what will be the output?
Yes. So measurement gate is basically uh, when you apply measurement gate, the state is getting collapsed. Uh, yes. Uh, what the question is not. I think I don't think question is correct.
Uh,
When we apply
Nasim,
the measurement gate on
if
any
you're there, can
particular
you be a little more
gate,
specific
it will
about the
collapse
question?
into one state only. Yeah.
Yeah.
Yes, sir. Can you proceed to the next question?
Is there any more questions?
we can conclude the session, sir.
Okay. So if there is any more, not any more questions, we will conclude these sessions. I would like to thank all the participants for their attendance and their enthusiastic response in the questions as well. And I would like to thank Mr. Tilak also for giving a wonderful talk. We'll be meeting or we'll be coming back to the next sessions. We have a lot of sessions in the pipeline. So we'll be meeting you all in the next session.